Hi everyone, I'll be presenting a talk about testing in a box. So a bit about myself. I'm a software engineer at CodeThink, and I've been working with them for almost a year and a half, and I specialize in embedded hardware and software. A bit about today's talk. I'll be starting by providing a bit of context about testing and what did we set as our requirements for this project, and finally the actual testing in a box implementation. So, a bit about CodeThink. CodeThink is a software consultancy based off in Manchester. We have been in the services business for almost 15 years. We leverage open source to solve problems for our clients. And we got clients in diverse industries, and many of them happen to be in the automotive sector, and some of them in the financial sector. We do get involved in various aspects of our clients' software products, but we also in most cases, end up solving problems related to built-in integration. And to be able to solve those built-in integration problems, we need rigorous testing. So let's talk about testing. So this slide has a diagram which talks about something we call as the testing progression. And in testing progression, we have tests on the left-hand side, which are quite easy to run. And as we step through the testing progression, we get tests which gets harder to run, can be more expensive, and but are very close to the actual production application. So developers do not want to write bad code. Developer wants to provide as much value as possible, and to be able to do that, we want mechanisms for us to allow the same workflow. So we want tests on the left-hand side to be as representative of the actual production application. But to get to the right-hand side, we usually have certain constraints. We will find tests which are slow to run. They have a higher time and time cycle. We have tests which can be quite manual because the actual infrastructure required to run them is quite complex, or to actually automate their tests, the infrastructure required isn't available. So people or clients will have tests which will require manual testing. Some of the tests can be quite expensive to run because they have expensive consumables, and sometimes we have tests which require quite resource-constrained hardware. For instance, in automotive application, you can have actual rigs, which are cars, and you can only have so many test cars, and only so many people can test on them in certain places. So our actual goal with our product is to make the tests on the left-hand side as accurate as possible, while making the tests on the right as accessible as possible. So what sort of tests do we want to do on hardware? We definitely want to be able to do full rig flashes. We want to be able to test OTA updates. We want to be able to do UI interaction and validation tests, which is a way in which a user is going to interact with the actual car in this case. And when a user interacts with the entire system, there are certain things that talk to each other, so you want to be able to validate how the entire network in the car works. For instance, that will involve CAN, SPI, Ethernet in certain cases. So this gives us a set of requirements for our testing methods, which will involve CI-only rigs, which means that we want to make sure that no code ends in mainline or lands in mainline until it is actually tested on hardware which represents the actual production application. We also want to have some sort of test coordination or test automation coordination, which will ensure that when we are running tests on constrained hardware or scarce resource, we are making the best use of it. And we will also need some sort of external tooling which will mimic the actual production application. So this gets us to the requirements for a basic testing infrastructure. In the most basic test infrastructure, you will require a mini PC of sorts to actually run tests against your hardware in loop or device in test. You will also need, as I mentioned, hardware to simulate the actual production application. So CAN dongles, which for the network, it's nice to have the ability to be able to flush your embedded targets in CI. So JTAG can help you do that. It can also help you gather data about your device in CI. Sometimes in test images, you'll have the ECUs will have serial enabled, so you can probe and get more debug information out of them. So you have one or various serial dongles. And sometimes the test application is so niche that off-the-shelf hardware has to be hacked beyond reason to be able to get a single working example. Here is one of our attempts at making using off-the-shelf hardware to make a USB switch. So to bring a bit of context, we had a client who was testing discovery of Android Auto and Apple CarPlay on their cars, very common feature in modern cars. So to actually test that, they were employing manual testing methods wherein engineers would have a spreadsheet with a set of requirements, and engineer would go up to the rig, plug in an Apple device, monitor and write down the actual output from the rigs, and based on that make a decision if the software is good enough or not. And that's based on the description. You can definitely find out that that's a solution to a problem that cannot and will not scale well. So we automated that process by first having an MVP, and then making custom hardware as a last resort, which looked something like that. So we made a USB switch, which is a bidirectional USB-C switch, which allows you to connect one host to two peripherals and vice versa. It's completely open source hardware made in KiCad, and you also get firmware and the case, which is also in the product repo. It supports USB super speed. Now that's something we have tested ourselves. That's not something we have certified against. And recently, we also put in the effort to get the USB switch EMC tested. It did pass the test, and we're currently in a process of getting those documents in the open. So you have put together, you got your mini PC, you got the required hardware, you put it all together, and your resulting infrastructure looks something like that. A key, I would say, key description of this hardware, of this setup is that it's functional, but it has a lot of capability, but it will confuse you when you're trying to set it up for the first time. You try to replicate it on multiple rigs is going to be a bit hard, and you have to maintain a bill of material, you have to maintain the documentation to put it all together. Overall, it's going to be trouble maintaining something that you hacked together in the first place. So that begs us to ask the question of what are the requirements for a robust testing infrastructure. So when we talk about long-term software support, we cannot discount the maintainability of the support and testing infrastructure, which means we want to be able to control and manage the inventory of spares. If you're putting in the effort to buy off-the-shelf hardware and putting in the effort to integrate the required tooling that comes with that piece of hardware in your testing infra, and that thing becomes unavailable after 2 to 3 years, then you have to invest more time into a different solution, which then means more time, which means more money. So we also want our testing infrastructure to be as easy and plug and play to set up, because we want our developers to spend more time actually using and consuming those tests rather than be able to setting those tests, the infra around those tests. And we also want the testing infra to be as consistent as possible, because consistency means that you reduce the variability in your setup, which then helps you debug your it basically reduces the ability to, it helps you debug better. So keeping those considerations in mind, we worked on our own solution and called it Testing in a Box. So testing in a box can be seen as a multi-tool for testing. It supports various kinds of I/O that might be required for testing on various things. It's quite modular by design. I think the image in this slide depicts the modularity in a much better way. So each layer in this image is what we call a slice. At the base of this slice, we have an ARM SBC. On top of that, we have a slice which holds the USB switch. On top of that, we have a slice which holds CAN dongles. And on top of that, we have a custom-made I/O board. I'll be talking about that in more detail in the future slides. And being modular, you can actually stack various slices on top of each other. So that means that you can have multiple USB switches if you want, or you can have more CAN dongles if you like. Or if you don't want them at all, you can take them out of your stack. So in the most basic setup, or the most basic stack configuration for testing in a box, it can be a GitLab runner. It can have it can be an OpenQA worker to enable UI tests. You have the ability to test device discoverability by plugging in and out USB devices programmatically. And you can monitor and mock your canvases. So basically, we try to check all the boxes that we set for ourselves in the initial list of requirements. So here's the fun part of the custom I/O board. So we have, on this custom I/O board, we have 3x FTDI FT232Hs, which gives us serial, which gives us SPI I2C, and JTAG. And then we have an RP2040, which does HID emulation. We have 3 USB 2 hub ports. We have an ESP32C3, which gives serial inputs to the RP2040, and also helps you flash the EEPROMs for the USB hubs to give it the right VID PID. And you have optocouplers on the top if you want to electronically isolate your board with your actual device under test. And this board is version 1 Rev B. Now, these are the changes we're going to make towards the version 2, wherein we're going to replace the 3 FT232Hs with an FT4 232H, which gives us 4x serial and 2s MP SSE, which basically means 2x ability to do I2C, SPI, JTAG. We'll be removing the ESP32C3 because, again, the version 1 of the board was very much experimental, and we didn't see the use of having the board there, so we'll be shifting that functionality of the ESP32C3 to the RP2040. And because we'll be reducing the amount of USB devices we're going to have, we can also get rid of one of the USB hubs. So the idea behind the version 2 of the board is to actually reduce the BOM cost and the part list, so that we make more space, and while keeping the same functionality as the version 1, given the more space we're going to make, we're going to add more functionality, which will involve having USB PD. So you'll be able to simply plug in a barrel jack to the board and then have USB PD coming out of it, so you can power other SBCs or device under tests from the board itself, which can be useful for low-density board farm applications. I've said a load of words in the previous slide, so here is a quick overview of the changes we're going to make. So that brings us to an example use case of testing in a box that we have at CodeThink. This also shows the modularity of testing in a box I/O board, or the stack in general. In this case, we're just using the I/O board, which is connected to a laptop, which in this case had to be an x86 system. So we have a laptop which connects to our device under test, in this case, which is the Orin. We have a capture card to capture the output from the Orin and do tests against, and that is basically our device under test and our hardware loop. So without going into detail about the actual example, I'll go into details about the developer's workflow with this example, and which is that as soon as a developer is happy with the changes he has made, he can initially test it on his own system, which is in QEMU. But then, when he's happy with his changes, he can make a merge request, and that merge request will run a set of pre-merge tests, which will flush the Orin. And to be able to flush the Orin, we have the I/O board, which then sets the right GPIOs on the Orin to put into recovery mode, flush the rig, run tests on the hardware, and based on the observation made, the CI will pass or fail. But that will give the developer enough feedback that, OK, the changes that I've made is affecting the system in X way. And if if your CI pipelines are green, that gives the reviewer another metric to test against or be to verify before he actually approves your code. And you can make sure that you have tested your hardware in emulation, and then whatever is landing in mainline is at least tested on a piece of hardware or your target. So hardware is only as good as the software that comes with it. So we bundle Ansible scripts with GitLab, which will help you set up GitLab runners, OpenQA workers, and we'll have CI templates. We also have scripts for you to set up the right UDEV rules for the I/O board, and we also have an example to set up, an Ansible script to set up the example with AGL. So all you bring is a Raspberry Pi running standard AGL, and all you do is put the QAD binary in the right place. I'll be talking about this in a minute. So the QAD binary goes in the right place in the rootfs, and when you set up this test, you instantly get AGL running against doing UI tests, CAN tests, and generally testing the interaction with UI and what the outputs generated with that in the CI. Now, I've talked about OpenQA and QAD a bit. So OpenQA is a tool we use at CodeThink to do UI validation tests. And it's an open source tool. We do like it quite a bit within CodeThink. And we have made upstream patches to it. QAD is a tool we made to actually do remote control of the board, so be able to actually run UI input tests on hardware. So we wrote QAD ourselves. And we made Canvas, which is a tool which gives you remote control of the board of your hardware in the test, and also makes your life easier when you're actually making the UI tests. So what's next for this project? As I've already mentioned, we are making the version 2 of Testing in a Box I/O board. And currently in the stack, we have a layer which holds certain CAN dongles, which we buy off the shelf. But we would like to, because given how many clients that we work with and we use CAN dongles quite often, we want to be able to have a board that does CAN, and we don't have to, we can share knowledge between projects easily. So we're going to be making our own CAN FD expansion board for Testing in the Box. And it's a product in development, so there's much more to come. And if you want to be a part of the journey, please do scan the QR code. And yeah, that'll be it for today. So thank you. Any questions?